Dear students, my name is Dr. Amir Fawaz Zahoor, and in this series of videos we will learn about disconnection approach. Disconnection approach or retrosynthetic analysis is a very advanced subject, and it utilizes all the key concepts which we have studied so far in our previous classes. Disconnection approach is basically imaginary or theoretically breakdown of a molecule to simple commercially available molecules. And some of the important terms which we would come across are as, I would like to elaborate these terms using an example. For example, we have R1, R2. R1, R2 is connected through a bond. This is one molecule, and this molecule has to be synthesized. We call it as target molecule. So target molecule is the molecule to be synthesized. And then next term is disconnection. Disconnection is a wiggly line that disconnects a bond and disconnects two structural units. This is reverse of a real chemical reaction. So this is disconnection. As a result of disconnection, the next term is retrosynthetic arrow. Retrosynthetic arrow. This arrow shows the reverse of a real chemical reaction. So it is shown by this arrow. And then next term is synthone. When we disconnect a molecule, for example, we have studied previously, if A and B are joined together and they disconnect or undergo fission reaction, we have two types of fission, homolytic and heterolytic. In homolytic fission, we get radicals, and in heterolytic fission, we get ions. A positive, B negative, or other combination would be A negative, B positive. Similarly, when we disconnect here, we get R1 positive and R2 negative. These are idealized reagents because we are doing all this theoretically, and when we disconnect with a wiggly line and put a retrosynthetic arrow here, then we get these synthones. So synthones are idealized reagents. And then the term reagent. Okay, when we perform a disconnection and we get synthones, the purpose is to hypothesize the reaction that this molecule could be synthesized from these fragments. Now we have to give a real chemical which could be an alternate to these synthones. For example, R1Y or R2X, for example, they in principle would react together to give this molecule. So it means reagents are real chemical compounds which are alternate or chemically equivalent to synthones. So these are some important terms. Now we see some characteristics of a good disconnection. Characteristics of a good disconnections are, for example, in a series of steps during a total synthesis. For example, we want to prepare D as target molecule, and we suppose that it could be obtained from C, and C could be obtained from B, and B can be obtained from A, which is commercially available. While doing the synthesis, we have to use A converting to B, then B converting to C, and C converting to our target molecule. This characteristic explains that each of this disconnection should correspond to a known reliable reaction. Why we need that? Because, for example, if we have undergone 2 of these steps and now we want to convert C into D, and C is in our hands now. If this step is not a known or reliable reaction, then of course in order to increase the yield and outcome of the reaction, we have to optimize the reaction conditions, and while doing so there is a possibility to waste the compound. Therefore it is necessary for us to choose or pick a reaction which is known and reliable, so that nothing could be wasted. If we waste it, we have to repeat all the series once again. Secondly, we have to choose the reactions which should result in correct regio and stereochemistry of the products. For example, if there is any question of regio or stereochemistry, we have to choose for the reaction which results in the correct stereochemistry or regiochemistry of the molecule. The atoms should be connected together in the correct way, and that those pattern would be in the target molecule. So this is also an important point. Okay, next step is we should choose a step which is high yielding, and in this minimum side products should form. As a result, there is a greater possibility that we have the product in larger quantities on our hand. For example, if we have a longer series, even longer than this, 5, 8, 10, 15 steps, and each step we should have high yield and minimum side products would, if are formed, then in that case we can have sufficient compound for our next reactions. In general, a compound can be synthesized, or a total synthesis can be hypothesized by various number of alternative routes. Different synthetic routes can be used to synthesize same molecule. However, ideally we should have shortest possible synthetic route to synthesize the molecule. So these are some of the features which we should keep in mind while choosing a disconnection. Now we see why we need this subject. This subject is very important because we know that many of the modern medicines, they have been isolated from plants or natural resources, and in order to obtain large quantities of such medicine, we have to kill that plant, and which is not good for the environment. So we have to prepare such compounds in our laboratories to make it available or make them available for human beings. For example, we have quinine, which was first discovered in Peru, and it is isolated from bark of cinchona plant, and this is used as anti-malarial drug. Now imagine if we have to use still today directly from plant, and there is so many population on this world, so we have to kill so many plants in order to get required amount of this drug. Therefore it was about more than 150 years that people got it isolated from or used the bark of cinchona plant, and in 1944 first artificial quinine was reported. So this subject is very important because we have to synthesize a target molecule in laboratory and we have to devise its synthetic pathways. Therefore we should know disconnection approach or retrosynthetic analysis. Now the terms which we have used and this subject we will explain using suitable example. For example, first molecule is this one, and we disconnect from here and use this retrosynthetic arrow. We will get, as a result of disconnection, what we get synthones, the idealized reagents. It is not necessary that we use positive here, we can use negative here as well. And if we use negative here and positive here and negative here, positive here, then we have to see whether we have a real reagent available for this synthone or not. So for this, when we have a positive charge on carbon, it means we can use corresponding halogen or a leaving group there. Corresponding alkyl halide would be used. So X is representing a leaving group or halogen. Here, when we have a carbon having negative charge and it is attached to hydroxyl group, it is not so common to have a reagent for synthone like this. So this combination cannot be used, and we will use this combination. For this, when we have positive charge on a carbon which is attached to hydroxyl group, we will use corresponding aldehyde. And in this case, when we have negative charge on carbon, then we use corresponding Grignard reagent. So corresponding Grignard reagent will be used, and now we propose the synthesis of the molecule. This reaction occurs in dry THF or dry diethyl ether at -20 degrees centigrade. So this is the synthesis. So this was pathway 1 or pathway A. In this case, we had a secondary alcohol in our target molecule, and we know that aldehyde and Grignard reagents, when react together, give rise to secondary alcohols. However, except for the case of formaldehyde, if we have hydrogen here, then we can get primary alcohol. In other cases, we have secondary alcohol, the product of Grignard reagent as well as aldehyde. Secondly, why we use dry solvent here? Because when we have Grignard reagent as a nucleophile, then we have to choose dry solvent because they are very reactive and they can absorb moisture, they can take proton from the moisture, and by taking proton from the moisture they can be converted in corresponding alkane. Therefore, when they are converted into corresponding alkane, it means it has been quenched and its reactivity is now finished, or it is also not available as nucleophile. Therefore, also it is the property of ethers, THF and diethyl ether, then they can absorb moisture, and this moisture can quench the Grignard reagent. Therefore, we have to dry them with suitable chemical, and because it is highly reactive, we have to use lower temperature. So this is first pathway, first possibility. We can add, or we can in parallel make a list of synthones. For example, for this synthone we had aldehyde, and if we had R negative, then we can use Grignard reagent. Now we can propose alternative route, pathway B. Instead of disconnecting from here, we can disconnect from here as well, and again we would get AR negative, here would be positive, and again the other combination would be this one. But this we have just explained that this combination cannot be used because of this synthone. For this we use again Grignard reagent, and for this we can use corresponding aldehyde. So synthesis. Same conditions, dry THF -20, and we would get the target molecule. So this is now clear to you. Now we can try another pathway. This would be pathway C. Now we have tried disconnection from here, and now we can disconnect from here. If we disconnect from here, we get this type of synthone. For this, if we have a carbon having positive charge and it is also attached to a carbon with hydroxyl group, corresponding epoxide can be used. And for this, again Grignard reagent. Okay, so I add here as well. Now in this case, same conditions as before, dry THF and lower temperature, and we will get the target molecule. Now here if we see the reactivity of epoxide, epoxide is a 3-membered heterocycle, oxygen containing heterocycle, and it ideally should have 60 degree. It would be having 60 degree because it's a triangle, but because this is a tetrahedral carbon, and a tetrahedral carbon requires approximately 109.5 degree angle. So this difference causes ring strain, and as a result of this ring strain, they are opened up, they are attracted by nucleophiles. So nucleophiles attack and the ring is opened. So that's why we can use epoxides in this case. Okay. Now pathway D. In the last three methods, we disconnected the molecule from here, from this position, and from this position. But it is also possible that we can get a secondary alcohol by reduction of ketone. If we have a second ketone and we can reduce it using lithium aluminium hydride, we can make a secondary alcohol. Therefore, we can use this concept here as well. We use secondary ketone for this preparation of secondary alcohol. This process, in which one functional group is converted into the other functional group, is called functional group interconversion. And which reaction is this? We would get this alcohol by the reduction of this ketone. So this reaction would be reduction. And this can be used using enolate chemistry, because we know that when a carbonyl compound having alpha hydrogen is treated with a base, it converts into enolate, which is reactive for electrophiles, which reacts with electrophiles and gives C alkylation products. So in this case, we have this enthone, we can use AR or R because it is general, so it is not really important. However, we should continue from where we have started. So we will have this, and for reagent for this one is corresponding ketone, and for this one is corresponding alkyl halide. So I add here as well. When there is positive charge, we have Rx. X can be chlorine, bromine, or mesylate, because they are all good leaving groups. Now synthesis. In the first step, we add a base to make this ketone into corresponding enolate, and then at the second place we would add corresponding alkyl halide. And this ketone can further be reduced using lithium aluminium hydride or sodium borohydride, and we can get the target molecule. So in this example, we have utilized enolate chemistry, the C alkylation reaction of enolates, and from disconnecting here we got these synthones we got then for this synthone we have corresponding ketone. For this positively charged alkyl chain we have alkyl halide, and as a result of this synthesis we get the target molecule. Okay. Now we propose another pathway. We can also disconnect the molecule from here, and if we disconnect from there, here positively charged synthone would be obtained, and this would be negatively charged. Whenever we disconnect a molecule between beta and gamma, on beta carbon there would be positive charge because it gives rise to a substrate alpha beta unsaturated carbonyl compound which is suitable for conjugate addition. And for this, now we will not use corresponding Grignard reagent because that is too reactive. For this we have to use lithium dialkyl cuprates. So I will add here as well. This, and for R negative we can also use R2CuLi. And now the synthesis. This will be conjugate addition here. And again it can be reduced using lithium aluminium hydride to give the target molecule. And now another pathway. This will again be obtained from corresponding ketone, but we can use this ketone this time and disconnect from here. As a result of disconnection, we get positive here and negative here. So this would be a candidate for extended conjugation. So its reagent would be this, and here Ar2CuLi, again lithium dialkyl cuprate. Now synthesis. We get this alpha beta unsaturated ketone as a result of this conjugate addition of this nucleophile to this electrophile. And now to reduce these two bonds simultaneously, we have to use a Lewis acid copper iodide with sodium borohydride as reducing agent, and methanol can be used as solvent, and we will get the target molecule. So I hope you have understood today. In this video I have explained the basics of disconnection approach with one example, and I have explained 6 routes to synthesize this molecule. Each synthetic route has its own merit or demerit, and we should be able to compare all these routes. In our next videos we will explain all these things in more detail. Thanks.